This is the second in a series of videos about acids and bases in solution. In the last video, we talked about polyprotics, and in this video, we'll talk about salts. So we don't usually think of solids as acids or as salts, as acids or bases, but sometimes they can contain acidic or basic pieces. So we've talked about weak acids and bases previously in this chapter. And some weak acids and weak bases are ionic, meaning they have a charge. So here's an example of some that we've talked about. Weak acid with a charge, ammonium, NH4+, and a weak base with a charge, HCO3-, bicarbonate. And we know that all of these things have to get into solution somehow, and you cannot add an ion to solution. They don't exist as solids. Solids are neutral. So when we want to add one of these things to a solution, we need to add them in the form of neutral salts. They need to be crystallized without a charge so we can add them and get them into the solution. So for our two examples that we used above, for NH4+, sometimes that is found in the form of a chloride salt. And for our weak base formed above, that's often found in the form of a sodium salt, sodium bicarbonate. So what we need is we have these salts and we want to get those ions back. And we can do that because salts are strong electrolytes. And strong electrolytes dissociate completely in solution. So if we put a salt into the solution, it's going to fully separate into its individual parts. So if we put our ammonium chloride solid into solution, it's going to have an arrow that goes fully to the right to fully separate out into the ammonium ion and the chloride ion, so that that weak acid is available. And the same is true for sodium bicarbonate. It will fully separate all the way to the right into that sodium ion and our weak base, bicarbonate. All right, no problem. So this is easy enough when we can recognize some of these pieces as weak acids or weak bases, but it isn't always super obvious what a salt is going to do when it's put into solution. So that's what we need to figure out. So we have to determine whether a salt solution will be acidic or basic, and we can do that by looking up the Ka values and the Kb values for each of the different ions and their conjugate pair. By looking up the Ka and Kb values for each ion and its conjugate partner. The reason we look up the conjugate partner is that not all of these ions are going to be listed in a table. And so if we can't find the ion, we should be able to find its partner. One of those two we should be able to look up. All right, so here's our equation again for ammonium chloride. Let's take a closer look. and pretend as if we didn't know that ammonium was a weak acid. So we're going to take each of the different ions, and we're going to look at the ion and its conjugate partner. So NH4 plus, its conjugate partner, if we remove a proton, would be NH3. And we can look those up in a table, and we should be able to find a value for NH3 for sure, because NH3 is a weak base, and it has a Kb of 1.8 times 10 to the negative 5. And we may or may not be able to find a Ka for this, but if we can't, we know that we can find it using the Kw. Kw equals Ka times Kb. So we can calculate this Ka value, be 5.6 times 10 to the negative 10th. Okay, so there's a Ka value for the NH4 plus, and it's greater than 0, so that means that NH4 plus is going to be acidic. And the reason we had to look up NH3 is so that we could find the Ka for NH4. So this is going to be acidic. So now let's do the same for the chloride. So chloride's partner is going to be the strong acid HCl, hydrochloric acid. And we know that hydrochloric acid is strong, so its Ka is going to be infinity. It's going to be too huge to mention. And that means that if HCl is a strong acid, chloride is going to be a very, very weak base where the Kb is essentially 0. So that means our chloride is going to be a very, very, very weak base. So it's basically inert. It basically doesn't do anything because it's the conjugate of a strong acid. And so now if we look at our two ions that come out of NH4Cl, we have a weak acid and an inert counter ion. So this solution is going to be acidic. And we can do the same thing for the other one. You can probably do this process in your head once you become familiar with these ions, and you can recognize them as acids or bases. But for polyprotics, or for unfamiliar compounds, you'll need to go through it manually. Okay, so sodium plus, its conjugate partner is sodium hydroxide. And sodium hydroxide is a strong base. Strong bases have a Kb of infinity or very, very, very big. And their conjugate partners have a Ka of essentially 0. They're such weak acids that they're basically inert. So the sodium ion is going to be inert. It's not going to contribute to the pH of the solution. And then for hydrogen carbonate, you may recognize this as part of the polyprotic we talked about in the previous video. So this compound could gain a proton and become carbonic acid, or it could also lose that second proton to become carbonate. So to figure out if HCO3 minus is going to be acidic or basic, we need to consider both of its possible conjugate partners. So we can look up carbonic acid in a table. We see that it's a weak acid, and its Ka value, like we wrote on the previous page, 4.3 10 to the negative 7th. And we can find the Kb for hydrogen carbonate when it gains a proton to become carbonic acid. We can do Kw equals Ka times Kb and find 2.3 times 10 to the negative 8th. And then we need to look at the other option. The other option is HCO3 minus to CO3 2 minus. This is a weak base, and we can look up its Kb as 2.1 10 to the negative 4th. And then we can use that number and plug that in here with Kw to solve for the Ka. Ka for carbonates, for hydrogen carbonate, 4.8 10 to the negative 11th. Okay, so now instead of having one value for hydrogen carbonate, we have two. It can act as a base and it can act as an acid. So to determine what it does in solution, we need to figure out which of these Ka's is larger. So the Kb is 10 to the negative 8th, the Ka is 10 to the negative 11th. So the Kb is going to be the larger one for carbonate. So that means that when carbonate is in a solution, the solution is going to be slightly basic. And so for our full salts, sodium bicarbonate, we have an inert cation and a slightly basic anion. So we're going to have a basic solution. So your Ka and Kb values give you a lot of information. They allow you to find the Ka or Kb for a compound not listed in the table. And it gives you information about whether each of the ions in a salt compound is going to act as an acid or a base when it dissolves in solution. So that's information about hydrolysis of salts. In the next video, we'll talk about the common ion effect.